So hi, we are group number 7, and we would be discussing about and I am Dhruv, rule number 14, and we would be discussing about the field of charge particle in hyperbolic motion. We would be taking in account of special relativity also to solve the electric field lines and potential generated by the charge particle. As we know, in special relativity, a particle of mass m, if subject to a constant force F, undergoes an hyperbolic motion, we would be taking account of equation as z square is equals to b square plus ct square, where b is equals to mc square by f. F is a constant force. At time t is equals to 0, particle would be at z is equals to b, and it would be going towards t is equals t plus minus infinity, and achieving the speed of light. As we know, information can't travel faster than the speed of light, and it would be just along the main diagonal of asymptote tangent to the hyperbolic motion. As this article shows that the field lines appear to terminate in midair at xy plane, this would violate Gauss's law. It can't be true. Our task is to locate the error and fix it. This article is divided into five sections. In section 2, we would be plotting electrical fields with help of Gauss and Maxwell's law. In section 3, we would be taking in count of truncated hyperbolic motion, which would tell us more about the electric field lines and kinetic field and constant velocity field lines generated by the delta step function. In section 5, we would try to work out the potential of charge in hyperbolic motion, and we were in last section. I would be telling the naive calculation mix the extra terms which conclude the puzzle unresolved. The article wouldn't conclude anything, but there are appendices A, B, and C, which would talk about some algebraic details and extras, and we would be taking in account of a book by A's Angle, which would more talk about retardation potential.
Hello, myself Soham Mandal. I'll be explaining what will be the electric field of a charge when it moves in a hyperbolic path and how it looks like. Generally, in special theory of relativity, we say that when you apply a constant force to a particle, it undergoes in hyperbolic motion. I mean, it follows a hyperbolic trajectory. And here we want to calculate the electric field of this charge particle Q when it is at point B. Okay, so we want to calculate the electric field of this charge particle at x comma 0 comma z when the charge particle is at point B, this B. So B is coordinate is B, it's 0 comma B, means z equals to V. So this is the formula of the electric field under the consideration of the relativity, and here are the form r vectors, that is x cap plus z minus root under b square plus c t r square z cap. Here tr means the retarded time, so here the other vectors u, v and a vector. So here we come to a concept of retarded time. So the retarded time means in electromagnetism there is a source and an observer. So it means the time delay of observing a particular wavelength, a particular wave. So there is a source which emits some electromagnetic radiation, and it reaches to the observer after a time delay tr. Suppose, for example, when a charge is moving in a straight path and it suddenly stops, so there will be change in electric field. That change is observed after tr time delay to the observer, and obviously more closer the observer is, more less the time delay. So why this time delay generally occurs? The time delay obviously occurs because their electromagnetic wave travels in a finite speed, that is with the speed of light, that is 3 into 10 to the power 8 meter per second. So it will take some time to reach from one point to another point, though it is the fastest, but still it is finite, so it will take some time. So here is the general formula of the retarded time Tr. Retarded time is generally obtained by the distance traveled by the electromagnetic wave divided by the speed of electromagnetic wave, first by subtracting it from the time at which observer observes the electromagnetic wave. So this time, this is the t is the time at which the observer observes the electromagnetic wave, and r by c is the time. It is the time. It is means it is r is the distance traveled by the electromagnetic wave divided by the speed of the light. So from this we calculate this, we equate this r. This is the one equation of r, and here is another equation of r, and we equate this two equation, and then we get ctr, means generally we get the value of retarded time. So we generally, what we do, we put all these formulas, means all these equations, this ctr, a vector, v vector, u vector, into this electromagnetic into this electric field equation. Then we obtain this electric field equation, and for our convenience we transform it into cylindrical coordinate, so the electric field comes out to be like this in cylindrical coordinate. Yeah, and this theta z is a step function, means means this equation is only for z greater than 0, and for z less than 0, means this theta z will be 1 for z greater than 0, and for z less than 0 it will be 0. And so how from this equation of this electric field we find the we say that field lines look like this. So it's kind of, you can say, the circles which are centered at the x-axis, origin at the x-axis, and and it means, and the source is at point B, means it equals to B point, means from this there is a charge at point B, so it emitting electric field, and the electric field looks like this. So we say that as the charge is only at point B, so in rest of the space del dot E must be 0 in rest of the space except this point, because there is charge, so there will be flux, and we can say that charge enclosed by some imaginary Gaussian surface will have some flux. And in rest of the area we will say del dot equals to 0, because there are no charges here, anywhere there are no charges, so we can't make any Gaussian surface and find electric flux. But the main problem arises in this part. We say that let us consider just to the right of the z, right of the xy plane, the xy plane is perpendicular to the z axis, and we say that just right of the xy plane is just suppose right here, we at some distance, just a very small distance, it's a very small distance from the origin. So we say that then we find the electric field. What we do for the, due to the small distance we consider, we just put z equals to 0 here, and we find this electric field. And we consider a Gaussian pillbox surface, means a imaginary Gaussian surface, where Gaussian cylindrical surface straddling the xy plane, and center is at origin with radius r. So we make a Gaussian plane, and then we find the electric flux due to this Gaussian plane, and we know that electric field is this, and we know electric field is integration of V dot dA, and it comes out to be like this, that minus q by epsilon naught r square divided by r square plus b square. But wait, this electric flux is finite, shouldn't it be 0? So why? Because there are no charges at just at the right hand side of there is only this charge, this at B, but there are no charges here. So the means there is flux from a surface when a surface encloses charges. When we say the Gaussian surface encloses a charge, so there is a flux from that surface, but there are no charges enclosed by our imaginary Gaussian pillbox. So how could be there any electric flux coming out from that point, from that surface? So this is the problem we try to fix in the next section. Thank you.
Hello, I am Rahul Korram. I will be explaining the third portion of the of our topic. So in this portion, we are assuming that the acceleration does not extend all the way back to minus infinity, but it actually begins at some time t naught, which we are taking to be equal to minus alpha into b divided by c for some positive constant alpha, when the particle was at z of t naught is equal to b into square root of 1 plus alpha square, and had a velocity of minus alpha c divided by 1 square root of 1 plus alpha square. Before t naught, the particle was traveling with a constant velocity, and after t naught it experiences some force, because of which it follows a hyperbolic path. So in simple words, the position of the particle is governed by these two equations. So at time t is equal to 0 for all points outside the sphere of radius alpha into b. So we are talking about this the sphere, this sphere, and we are talking about the points outside this sphere. So the field is that of a charge moving at a constant velocity had it continued on its original flight plan. So this so the straight lines, these straight lines are actually coming out of these equations, uh, and the curved electric field lines are due to the accelerated um, motion of the charged particle. So the left edge of the sphere is at uh, 1 plus square root of 1 plus alpha square minus alpha whole multiplied by b, which is always positive but goes to 0 as alpha tends to 0. Inside the sphere, where the news of acceleration is has been received, the field is given by this equation, which is this equation is derived in the second portion. So the field lines evidently join up in a thin layer at the surface of sphere. So the field lines, these we are talking about these field lines, these uh, uh, these joined up in a thin layer outside the surface of the sphere, outside the surface of the sphere, uh, which motion switches representing the brief interval during which the motion switches from uniform to hyperbolic. So this is uniform and this is hyperbolic. So the thin layer is actually we are calling it a connecting field, which is connecting these two types of motion. So as alpha increases, that is as t naught recedes into the more distant past, the radius of the sphere, which was alpha into b, increases, and its left surface uh, flattens out against the xy plane. The xy plane is perpendicular to z, so we can say that xy plane is like this. So meanwhile, the outside field compresses into a disk and perpendicular to the motion. So motion is happening in this. So perpendicular to motion means this. So and squeezes also onto the xy plane. The complete field lines, the complete field lines now execute a 90-degree, turn at z is equal to 0. So as z is equal, the field lines approaches z is equal to 0, it completely executes at 90-degree turn as required to rescue Gauss's law. Indeed, for alpha tending to infinity, the constant velocity portion of the field approaches that of a point charge moving at speed c, which is given by this. But this is not what was needed to cancel the flux. When we will calculate the flux will still not equals to 0. So what are we lacking? So it turns out that the connecting field, which we were ignoring first, plays here a major role. So uh, the connecting the net field in the xy plane actually consists of two parts: the field E dash due to the portion of the motion at constant velocity given by this equation, and the connecting field that joins it to the hyperbolic part. So the actual electric field is the sum of these fields. The true field of a charge in a hyperbolic motion then turns out to be this equation. So let's check out whether it is true or not. So for validating this equation, we validating this equation, we uh, calculate the divergence of this electric field, which should be equal to rho by epsilon naught, which is Gauss's law. So when we calculate the divergence of this, when earlier we are calculating the divergence of this it was coming out to be 0, but here the divergence comes out after doing some mathematics. It turns out to be rho by epsilon naught, is which is valid, which is actually Gauss's law. So the actual electric field of a charge in hyperbolic motion turns out to be q b square divided by 4 epsilon naught into bracket z square minus s square minus b square bracket close z in z direction plus 2 times z s in s direction divided by but the electric field turns out to be this equation. So that's it for my part. Thank you.
Good evening, sir. My name is B.Shiva, and currently I am a third year B.Tech student at IIT Bombay. So my project topic is, sir, the field of a charged particle in hyperbolic motion. So I am dealing my part 4, part A. That's a linear Vicard potential. So actually the main point of this, sir, we have the electric field equation above. So I'm going to prove that equation, how we got that equation. So let's work like, so we know the retarded potential, actually it's there in above. So retarded position of charge point is the B1 equations are, and the retarded time is B2 equation. Formula for D is R minus R dot V by C. So after substituting R and V, we will get the B3 equations are, and squaring of B2 we will get the B4 equation, and substituting that B4 equation in B3 we will get the B5 equations are, and again squaring 2 times of B2 equation we will get the TR values are. So and this substituting this TR in the B5 equation we will get the complete equation of D, and we know the potential is Q by 4 pi naught into 1 by D. Substituting this D in the potential V, we will get this equation, sir, and we know the vector potential is V by C square into V. V and the formula for V is TR by under root B square plus TR square. So substituting this V and this potential, we will get the vector potential as this equation, sir. And here we are going to find out the electric field. So electric field is equal to minus gradient of V minus partial derivative of A. So the gradient of V is this one. Actually it's a long equation, so I could not solve the equation, so I just copied this one and pasted in some calculator, so I got these equations. And same as same for partial derivative of t also. So I got this equation, and the extra term I am getting 0 because the every term is cancelling, so I am not getting the extra part. So in order to fix that, we are doing the same, like truncating the hyperbolic motion, like the truncation receding to minus infinity with a point charge moving at the speed, like the so here, like when we are adding the derivatives of any scalar field and still get the same electric and magnetic field, and those two set of potentials only differ by such transformations called gauge transformation, then we are talking about the same physical situation. So we have to connect potentials of our expression with the field, like from equation 18 to equation 20. Those are like q by 2 pi e naught s by a square of delta z, and q by 2 pi e naught s by a square plus b square into delta of z. After doing that, ANSA suggests these potentials and the vector potential. One is 36 equation and the another is 37 equation. 36 equation is 0, potential is 0, and the vector potential is minus q by 2 pi e naught c into s by a square plus b square into theta of z plus t. And 37 equation is v minus q by 4 pi e naught ln of a square plus b square by b square into delta of t plus z, and vector potential is q by 4 pi e naught c ln of a square plus b square by b square into delta of z plus t into z cap. So comparing both electric field equation and this equation, if we add this term, then we will get the potential v and a which satisfy the electric field equation. And the equation 37 satisfy, like, it preserves the Lorentz gauge. So if we add these things, then we will get the exact electric field, and these 37 equation is satisfying those conditions. So we will get this potential and the vector potential as q by 4 pi naught 1 by t square minus z square into t minus z into a square plus z square plus b square minus t square divided by under root 4b square into t square minus z square plus a square plus z square plus b square minus t square whole square into theta of z t plus z minus ln of a square plus b square divided by b square into delta of z plus t. And the same, and we got the equation of vector potential A. So if we put these equations in the electric field equation, the electric field is equal to minus gradient of V minus partial derivative of A. So then we will get the exact electric field as we got before. So thank you, sir. This is my part, and the next part will taken by some other guy.
Hello, I'm Ihsaan Hussain and I'll be doing the retarded potentials part of this paper. So we have the retarded potential equation V is equal to 1 by 4 pi epsilon integral rho by r d3 r dash, which we derived in class. This r is mod r minus r dash. And in our case, rho will be q into Dirac delta in 3 dimension, r minus root b square plus ct the whole square. And then retarded time for t is equal to 0, we get this is t minus tr is equal to mod r minus r dash by c. So at t is equal to 0, we get minus ctr, which is equal to mod r minus r dash, and this is root over x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square. And then when we put this into the charge density, we get q into del 3, and this is r minus root b square plus ct whole square. So your r dash, that becomes x dash plus y dash plus z dash, and your b square plus ct whole square, you get b square plus ctr. This is this part, and this r is equal to minus ctr, and this is equal to minus tr. This tr which we got in the Lennard potentials part. So this, in this tr, when we put t is equal to 0, we get this part, and this is equal to this r mod r minus r dash. So that so this comes out of the integral, and we only have to do the integral of this rho d3 r dash. And then your del 3 r is equal to del x del y del z. So when we convert it, we get del x dash del y dash, this part you get del x dash del y dash and del z dash minus root over b square, and this part we get this part. And then when we integrate with respect to x dash, the x dash goes to 0, and then with respect to y dash go to 0, and we get this del of z dash minus root over b square plus s square plus z minus z dash whole square. And then we take this as f of z dash, which is this part, and then all of this equal to a value q. Here s is root over x square plus y square. And then to solve this Dirac delta of a function, we need the root and the derivative. So first we find the root, and that f of z dash, when it's equal to 0, your argument of Dirac delta function goes to 0. So let the root be z naught. So we have z0 is equal to root over b square plus s square plus z minus z naught whole square, which we get from here. Here this goes to 0, you get z0 is equal to b square plus s square plus z minus z0 whole square. And when we solve it, we get z0 is equal to 1 by 2z s square plus z square plus b square. And here z0 cannot be negative. So when z is negative, z0 there is no solution. And then we take the derivative of f with respect to z dash, you get 1 plus z minus z dash by root over b square plus s square plus z minus z dash whole square. And when we put z naught to this equation, we get 1 plus z minus z naught by root over b square plus s square plus z minus z naught whole square. This is whole square. And then this root over b square plus s square plus z minus z naught, which we got over here, is just z naught. So you get 1 plus z minus z0 by z0, and this is z by z0. And here we got z0, which is this. We put this here, we get 2z square by s square plus z square plus b square. And Dirac delta of a function we know is sigma del by df by dx, where ai is the roots. So we do this here as well for f of z dash. We get 1 by f dash z naught into del z dash minus z naught, which is f of z naught, f of z dash, this part. And then we get this equation. And so when we integrate this, we get s square plus z square plus b square by 2z square. So your q, which is this, q is equal to q into s square plus z square plus b square by 2z square. And here theta is the step function. When z greater than 1, it's 1, and if z is negative, it will be 0. And this will give us the potential function, which is equal to 1 by 4 pi epsilon, which 1 by 4 pi epsilon, and you have the rho by r. So we have the rho, which is q into s square plus z square plus b square by 2z square by 2z square. And then we have the r, which we derived before, this 1 by 2z root over s square plus z square plus b square whole square minus 2bz the whole square. And then we get the potential, and this potential matches the Leonard potential which we did in the earlier part. When we put t is equal to 0, it matches the Leonard potential, but it does not match the corrected Leonard potential which we got for when we truncated the hyperbolic motion. We had the extra term here, but there doesn't seem to be that extra term in this retarded potential. So this shows that the retarded potential itself is wrong, and it's incorrect in this case. So yeah, thank you.
Leading to the final part of the article review, we would look about to the LW potentials and inconsistency with Maxwell equation in case of charge particle and hyperbolic motion, and their essential delta function missing contribution, which would be taking in count of the book by A. Zangwill, and we would carefully construct configurations for which the retard potential breakdown, and we know other cases to find the field formula. So retardation. The finite propagation of speed of electromagnetic waves guarantees that changes in behavior of source can't be detected simultaneously, cause the phenomena that the cause happens before the effect. This phenomena is called retardation. It connects electromagnetic field in a fundamental way of time varying distributions of charge and current that produce them. So here we are trying to fit special relativity into the Green's function so that we can take in count of that retardation potential. The general solution of in a homogeneous phase. The thing I said, it explodes Green's second identity. It adds 1 by c square term extra in Green's function from time t1 to t2, and t dash is t minus r by c. We resolve exactly the same issue in electrostatics by suitable choice of special boundary conditions, Dirichlet and Newman, for the Poisson-Green function. Here we are assumed that a special boundary term is absent. Becomes a useful formula when we make a suitable choice of temporal boundary conditions for the Green function. They came to the result that g plus minus r comma t is equals to 1 by r g plus minus t plus minus r by c, where g plus g minus r arbitrary is a function for of one scalar variable. Now apply the Now they are going to apply bracketed operator left side of using 20.3. After putting r is equals to r minus r dash and t is equals to t minus t dash, they arrive to this solution. Now we are taking in count of retarded ways and advanced ways. Uh, we add one more term. Time is equals to t minus r by c. And they conclude the spherical potential to be d3 cube g minus r minus r dash comma t minus t dash f of function of r dash comma t dash equals 1 by 4 pi d3 r volume integral f r dash comma t minus r minus r dash by c upon r minus r dash mod. There is a very happening encounter between Ritz and Einstein cause of this non-causal nature in advanced potential. The Swiss physicist Walter Ritz debated whether physical principle, the retarded potential alone, must be used to discuss electromagnetic phenomena. Ritz argued that retarded potential is chosen by nature to distinguish the past from future. There's a choice of underlies the second law of thermodynamics, which I also don't believe, because cells consume and we live, and it's not possible. Einstein asserted that the advanced and retarded potential are equally valid for use in an infinite volume of space, and that the origin of the second law should be sought in laws of probability. Uh, uh, Ritz died of tuberculosis at the age of 31. Typical Einstein's fellows. Retard weighs the time harmonic sources. Here we take in counts of some imaginary attributes. Finally, we came down to introducing a new Hankel function, which would be acting as a step function for our determining the potential and fields in the Green's function, which goes g naught is equal to rho by rho dash is equals to I by 4 h naught 1 k minus rho naught. Retardation for potential and fields. The electronic field and magnetic field are retarded function of the time-dependent charge density and current density which produce them. Here they produce Hertz voltage potential functions for the usual scalar and vector potential. The retarded Hertz potential which satisfy the inhomogeneous wave equations, and they came to conclusion that potential for electromagnetic field is 1 by 4 pi epsilon naught volume integral dipole r dash minus t minus r by c upon r mod, and magnetic field as mu naught by 4 pi integral volume integral um, m r dash t minus r by c r mod. In the column gauge, the vector potential satisfies the inhomogeneous wave equation, and thus vector potential has a retarded presentation. However, the column gauge scalar potential satisfies the Poisson equation, for which the relevant particle solution is the usual Coulomb integral. The latter connects the scalar potential at time t to the charge density at time t. There is no retardation for this quantity, and nor need there be, because the potential function of electromagnetics are not observables. The observables are fields B is equals to gradient of AC, and E is equals to minus AC by dt, which the reader can confirm by direct calculation or are properly retarded. Finally, the retarded Lorentz potential lead straight forwardly to a retarded expression for the electric field and magnetic fields. To derive them, they assume R to be R minus R dash and T relatively be to is equals to T minus R by C. They finally reach the conclusion to electric field to be 1 by 4 pi epsilon volume integral rho retarded R by R cube plus R by C R square differential rho retarded by D by dt minus 1 by c square r d j r d by dt, and magnetic field to be mu naught by 4 pi volume integral uh, j rt r cube plus 1 by c square j rt dt cross product r. They reiterated that the retardation of magnetic field and electric field with respect to their sources is a consequence of 20.4 and 20.5, and does not depend on the fact that we used retarded Lorentz-Gauge potentials to derive 20.68 20.69. As noted earlier, particle retarded column Gauge potentials lead to exactly the same result. This is a consequence of the Gauge invariance of electromagnetism. Now back to appendices. We would take in count of the first part, retarded time for points the xy plane. We took tr to be t square minus a square by 2t, where a square goes to x square plus y square plus b square by c square, which plotted the following graph. Then we take in count of some hyperbolic conditions, which introduce us to different electrical field lines, and we tried to solve them, and it came out to be three solutions for this. After this, uh, we tried to work out some potentials, which is r is equals to s by s comma z, and the denominator comes out to be tr by under root 1 b square plus tr square. We can find potential by kq by b, and vector potential by v c by c square multiplied by vector multiplied by potential. In appendices C, they find out radiation by integrating the Poynting factor with S is equals to 1 by mu naught electric field cross product magnetic field. Finally, electrical field and magnetic field are QB square by pi epsilon naught z square minus s square minus b square minus t square z cap plus 2z s uh, bracket z square plus s square plus b square minus t square whole square minus 4b square z square minus t square whole power 3 by 2 theta z plus t. This is step function. Q by 2 by epsilon naught s by s square plus b square delta z plus t, which is the delta function. And magnetic field to be qb square by pi epsilon naught c, which is 1 by c r vector cross cross magnetic cross electrical field. Same delta function and step function. This came out to be s dot dA with r with for sphere r square sin theta d theta d phi, and radiation came out to be cq square by 6 pi epsilon naught by b square, uh, which is q square by 6 pi epsilon naught cq gamma power 6 a square. Thank you.